Computational Topology, an Introduction by Herbert Edelsbrunner and John L. Harrer. Section 1.2, Curves in the Plane. In the previous section, we used paths to merge points into connected components. To capture aspects of connectivity that go beyond components, we need different maps. Closed curves. We distinguish primarily between two kinds of connected curves, paths and closed curves. We defined in the previous section, paths are continuous maps from the interval 0 to 1 to x. Sometimes a closed curve is defined as a path in which 0 and 1 map to the same point. Usually, we will define a closed curve to be a map from the unit circle, gamma, mapping S1 to x, where S1 equal the set x a member of R2, such that the norm of x is equal to 1. This second version emphasizes the important fact that paths and closed curves capture different properties of topological spaces, since the interval and the circle are different topological spaces. To make this precise, we call two topological spaces homeomorphic, or topologically equivalent, if there exists a continuous bijection from one space into the other, whose inverse is also continuous. A map with these properties is called a homeomorphism. Notice that a homeomorphism between two spaces gives a bijection between their open sets. The unit interval and the unit circle are not homeomorphic. Indeed, removing the midpoint decomposes the interval into two components, while removing any point leaves the circle connected. This contradicts the existence of a bijection that is continuous in both directions. Figure 1.3, the shaded inside and the white outside of a simple closed curve in the plane. Considering maps into the Euclidean plane x equal R2, it makes sense to distinguish curves with and without self-intersections. A simple closed curve is a curve without self-intersections, that is, a continuous injection, gamma, from S1 to R2. Interestingly, every such curve decomposes the plane into two pieces, one on each side of the curve, as in Figure 1.3. Jordan curve theorem. Removing the image of a simple closed curve from R2 leaves two connected components, the bounded inside and the unbounded outside. The inside, together with the image of the curve, is in fact homeomorphic to a closed disk. This may seem obvious, but proving it is challenged by the generality of the claim, which is formulated for all and not just smooth or piecewise linear simple closed curves. There are reasons to believe that there is no simple proof for such a general claim. The fact that the inside together with the curve is homeomorphic to the closed disk, B2 equal the set x a member of R2 such that the norm of x is less than or equal to 1, is known as the Schonfly's theorem. The Jordan curve theorem remains valid if we replace the plane by the sphere S2 equal the set x a member of R3 such that the norm of x is equal to 1, but not if we replace it by the torus. The Schonfly's theorem, as stated, is false in dimensions higher than 2. Parity Algorithm. Given a simple closed curve in the plane, a fundamental computational question asks whether a given query point x, a member of R2, lies inside, on, or outside the curve. To write an algorithm answering this question, we assume a finite approximation of the curve. For example, we may specify gamma at a finite number of points and interpolate linearly between them. The result is a closed polygon, see Figure 1.4. It is simple if it is a closed curve itself. Figure 1.4, approximation of the simple closed curve in Figure 1.3 by a simple closed polygon. The point x lies inside the polygon, and the half line crosses the polygon an odd number of times. To decide whether the point x lies inside such a simple closed polygon, we draw a half line emanating from x and count how often it crosses the polygon. Assuming x does not lie on the polygon, it lies inside if the number of crossings is odd and outside if that number is even, hence the name parity algorithm. In the implementation of this idea, we let x equal x1, x2 be the query point. and A equal A1, A2, B equal B1, B2 the endpoints of an edge of the polygon. We assume the generic case in which no 3 points are collinear and no two lie on a common vertical or horizontal line. To simplify the code, we choose the horizontal half line leaving X toward the right and assume that A is below B. That is, A2 is less than B2. We first make sure that the entire horizontal line crosses the edge, which we do by testing A2 less than X2 less than B2. If it does, we test whether the crossing lies to the left or to the right of the query point. To this end, we compute the determinant of the matrix delta of x, a, b equal the matrix 1, x1, x2, 1, a1, a2, 1, b1, b2, which is positive if and only if the sequence of points x, a, b forms a left turn. To see this, we verify the claim for x equal 0, 0, a equal 1, 0, b equal 0, 1, and then notice that the sign of the determinant switches exactly when the 3 points become collinear. We use this fact to decide whether the half line crosses the edge. Code: Boolean does cross parameters x, a, b. If not a2 less than x2 less than b2, then return false, end if. Return the determinant delta of x, a, b greater than 0. Now, we run this test for all edges, and this way count the crossings. The trouble with this implementation is the non-generic cases. We finesse them by using two infinitesimally small positive numbers, 0 less than epsilon sub 1, strictly less than epsilon sub 2, and substituting x prime equal x1 plus epsilon 1, x2 plus epsilon 2 for x. A generic case for x is generic for x prime, and we get the same decision for both points. A non-generic case for x is generic for x prime, and we use the decision for x prime. Polygon triangulation. Sometimes it is useful to have a more structured representation of the inside of a polygon. For example, for navigation to find the exit out of a maze. The most common such structural representation is a triangulation, which is a decomposition into triangles. Here we require that the triangles use the vertices of the polygon, but do not introduce new ones. Furthermore, they use the edges of the polygon together with diagonals, which are new edges that connect non-adjacent vertices of the polygon. The diagonals are required to pass through the inside and not cross any other diagonals and any polygon edges. See Figure 1.5. Figure 1.5. A triangulation of a polygon in Figure 1.4. Each diagonal passes from one side of the inside to the other. To prove that a triangulation always exists, we just need to show that there is at least one diagonal, unless the number of edges in the polygon is n equal 3. Indeed, we may consider the leftmost vertex, B, of the polygon. Either we can connect its two neighbors, A and C, or we can connect B to the leftmost vertex U that lies inside the triangular region ABC. Drawing this diagonal decomposes the n-gon into two, an n1 gon and an n2 gon. We have n1 plus n2 equal n plus 2. And since both are at least 3, we also have n1, n2 less than n. We can thus use induction to complete the proof. The same inductive argument shows that there are n minus 3 diagonals and n minus 2 triangles, no matter how we triangulate. This is suggestive. Indeed, we can think of the triangles as nodes and the diagonals as arcs of a tree. Since every tree with n minus 2 greater than equal to 2 nodes has at least one leaf, that is, a node with only one neighbor. Every triangulation has an ear, that is, a triangle formed by one diagonal and two polygon edges. Incidentally, this is another property that does not generalize to tetrahedral decompositions in R3. Winding number. We return to a general, not necessarily simple, closed curve gamma mapping S1 to R2. Let X be a point not in the image of the curve. Suppose that we transverse gamma and view the moving point from x. Specifically, we let S go around the circle and observe the unit vector gamma of S minus x divided by the norm of gamma of S minus x rotate about the origin. When the vector completes a full turn, we count +1 or -1 depending on whether this turn is counterclockwise or clockwise. The sum of these numbers is the winding number of gamma and x, denoted by W of gamma, x. It is necessarily an integer and gives the net number of counterclockwise turns we observe. If gamma is simple, then the points inside the curve all have the same winding number, -1 or +1. To reduce this to one case, we may reorient the curve, for instance by reflecting the unit circle along the horizontal coordinate axis, and get W of gamma, x equal +1 if x is inside, 0 if x is outside. However, for non-simple curves, we can get winding numbers of absolute value larger than 1. See Figure 1.6. Suppose we move x in the plane. As long as it does not cross the curve, the winding number does not change. Figure 1.6. An oriented, non-simple closed curve with regions distinguished by the winding number of their points. Crossing the curve changes the winding number, namely by -1 if we cross from left to right, and by +1 if we cross from right to left. But this implies that at least two regions in the decomposition defined by gamma have their boundary arcs consistently oriented. Specifically, the neighbors of a region with locally maximum winding number all have winding number 1 less, so the region lies to the left of its boundary arcs. Similarly, a region with locally minimal winding number lies to the right of all its boundary arcs. Bibliographic notes. The Jordan curve theorem is well known also beyond topology, in part because it seems so obvious, but at the same time is difficult to prove. The theorem is named after Camille Jordan, who was the first to present a proof in 1882. This proof was later found to be incorrect, and the first satisfactory proof is due to Veblen, 145. We refer to 151 for a more recent discussion of this result. The difficulties encountered in the implementation of the parity algorithm for locating a point inside or outside a closed polygon have been voiced in 71. A provably correct implementation can be achieved with exact arithmetic and symbolic perturbation as described in 62. Triangulations of simple closed polygons in the plane have been studied in computational geometry. Constructing such a triangulation in time proportional to the number of vertices seems rather difficult, and the algorithm of Chazelle 32 that achieves this feat is not recommended for implementation. Analytic Conics by Barry Spain, Trinity College, Dublin, May. Published by Pergamon Press, London, 1957. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.